Hello teammates, it's Mr. Ninny. This is what I am calling FRQ number 6 from 30 April. And we're going to do a little electric fields, electric potential energy. We got a lot going on. It took me 3 pages to write the solution to this. So let's go. Let me introduce. This is more of a review at this point before we dive into solving the problem. So we're told there's 2 charges, and we're given the isolines, and you recognize that shape. And you don't have to draw the field lines, but I did that to help you recognize what's going on. So you've got an electric dipole, if you recall back to our electric fields discussion. So the way these field lines go, they're moving away from each other. Field lines are always perpendicular to your isolines, and that's why you don't have anything coming like they're going away, aren't they? So it's easier for me to visualize. I've done this a little bit. You see how these, if I were to draw another field line here, it's going away like that. And you're not going to have electric field, right, come back like that. They're going to go in a clear path. Path, like anything in physics, very interesting. This law, this path of least distance that physical systems obey is absolutely fascinating. We're learning more and more about that, how that works, and how our understanding of forces, etc., is really this path of least distance that physical objects take. For another time, let's look. So so I did this to help me visualize. I recommend you do the same thing too if you're faced with that, and don't, right, because you could fool yourself, right? You could fool yourself. You could draw something like that, couldn't you? But you got to look at what's going on out here and how those field lines are going. And whoa, that was on my change. When you're dealing with field lines, just look at the whole thing. Don't get that target fixation. So let's dive into part A. I moved my camera. Maybe that was not a smart idea. So we're told 10 volts between each set of adjacent lines. The electric potential at the outermost line is 50 volts. And we're told that charge Y is positive. And you know that electric potential decreases with distance, right? Because we look at electric potential as it was acting on a test charge, and test charges are always positive, and so we know that we're just talking electric potential. We're just talking we're talking test charges. If that's 50, and electric potential decreases as we go away, and it changes by 10. Electric potential increases as we come closer. So if that's 50, 60, 80 on down. Yeah, so 60 volts for point A and 80 volts for point B. It's good. Let's go. YouTube cuts us off at 15 minutes, so I've got a race. Let me find something better to cover this with. Yeah, it's all right. So BI, how the magnitudes of charges compare. Charge Y has got more charge than X. We know this because the isolines are further for charge Y than charge X. And we know that electric potential can be represented by voltage equals K times Q over R. And if we rearrange, we know K is constant, so voltage is going to be constant. So the greater the charge, the greater the distance of our isoline. And I would tie it back to an equation with words. Just don't say electric potential because equation. And recall on your equation sheet, you got a funky representation for K. We'll talk about that. Not today. It's good. It's good. Let's look at the second part. We're going to talk about the electric potential. Isoline is perpendicular. Pattern of field indicates electric dipole. Same types of charge. Because sphere Y is identified as positive, sphere X must also be identified as positive. Double I, we can compare gravitational force to electric force. Right, you're going to talk inverse square. You're going to, so you're going to compare and contrast. They're asking you for one similarity, one difference. So similarity is inverse square, easy money. But don't just say again. Don't just say inverse square. Explain why that is. If you just write inverse square, you might not get might get anything for that. And what's different? You know the gravitational force is always attractive. Electric force can be attractive or repulsive. And explain why. If I put an object in between these two spheres, they would be attracted. It would be attracted to those two spheres gravitationally. If I put a charged object, it could be either attracted or repulsed depending on its charge. Easy money. Easy money. Yeah, I'm gonna keep going. That was 2 points. I answered C, and I think I might have answered C twice. It's good. D. We're on to D. Proton has moved through a potential difference of magnitude 20 volts. And we want to talk about that change. We're going to answer symbolically. And we're going to help that reader. We're going to help that reader help us get the high score. The motion, the proton is going to move away from the spheres, and so this potential is gonna decrease. We're gonna invoke our change electric potential equation. Change electric potential equals charge times change in voltage. We can then determine the change in potential as change electric potential equals Q times voltage at A minus voltage at B. So just like in the note I wrote there, is just like anything in physics, just like change of kinetic energies, kinetic final minus initial, change of velocity, final minus initial. Same thing. It's a pattern you're going to find throughout your physics career. Final minus initial, and we met our goal. C is just a distractor. They put C there in case you thought it was going the wrong way. So it's good. So again, when you're given those choices of variables, I was talking to the AP team yesterday, you might not have to use all the variables. Don't fall into the trap. That was 2 points. We did a lot of writing. D double I. D double I was fun. Brought back a lot of memories. Proton's going to be displaced some distance D. There you go. I'm very sorry. And we want to determine symbolic expression for the work done. There's two ways to do it. And I would walk them all the way through. I would go back to basic principles. Work is force times distance. Work is also your change in electric potential energy, right? So your change in kinetic energy represents the work done. You also know that work done for a charge system is Q times change in V, because electric potential energy is charge times change in voltage. You lose electric potential energy. So you got a couple ways. You can attack this by electric field strength equals force electric over Q. Rearrange. Now when they talk average, you can do this. It's I don't know. I'm not going to call it a trick, but if they're going to call it average, you're going to call it average. It's okay. You're not going to have to add a bunch of stuff and divide a bunch of stuff. And so force average equals electric field average times charge. And so you can rearrange this. So work equals force times distance. You identified force as E times Q. And distance, so now you got, this is your force, and that's your distance, and that's your work. You can also go change in V equals E average times D. These are in your equation sheets, not the average. You can put the average in. So work is force QV is your where would I go? Oh, there it is. Your change in V is there, right? So E field times D, and then that's your V from here, and then you bring your Q, and there you are. There you are. Hot diggity dog. Now you got two students. You got a discourse on the two systems. So the question tells you two students make a statement, and you're told discuss each student's claim. Read that carefully. You're going to discuss each student's claim. Don't fall into the trap and say, okay, student 1's correct, and ignore student 2. Because student 2 is also correct. So when they say evaluate each student's claim, you're going to say student 1, student 2. Student 1 is correct because by conservation of energy. If the energy is gained by the proton, it's lost by the system. Example, you got the charged object, you got the proton. There's some electric potential energy there. When the proton moves down the gradient, down the voltage gradient, your system loses electric potential energy, but the proton gains kinetic energy. I hope that makes sense. Your system is the charged object and the proton. Your system loses electric potential energy, but your proton gains kinetic energy, so energy is conserved. It's good. Student 2 can also be right. If the system's just a proton, there must have been external work done on the proton by work equals force times distance, which could cause an increase in the KE of the proton. I hope that's good, teammates. If you'd like me to take a picture and post these as well, please let me know. Have you a great day.